Hello and welcome back. We'll continue looking at this question about the roots of the polynomial x to the fourth minus 6x cubed plus 22x squared minus 30x plus 13. So from the picture, we know that, and from a little bit of our work, we know that the polynomial will only have one real root because there's only one place along the x-axis where the polynomial hits a line. But because it also comes down, touches and turns around, we know that the root has even multiplicity, meaning that 1 will be a root of this polynomial twice, 4 times, 6 times, 8 times, and so on and so forth. However, we can say a little bit more. It's either 2 times or 4 times. It can't be 6 times, 8 times, or so on, because our polynomial will only have 4 roots. We can't have more than four roots to a fourth degree polynomial. So even though it could be any even number of times, it's limited above. So it's either going to be 2 or 4 times. So we know that it's at least 2 times. So we know the following. Let me write this up here. 1 is a root at least 2 times, which means the following. F has this as a factor twice, meaning that I can divide f by this 2 times. So if I divide it by this and I divide it by this again, I should find that it's evenly divisible. Well, if I multiply this out, this is x squared minus 2x plus 1. So that means that this is a factor of f. Right above my head a little bit there. So let's divide our function. So I'll need to, minus 6 plus 22 minus 30 plus 13. We have x to the fourth minus 6x to the third plus 22 minus 22x squared minus 30 plus 13. And we're going to divide this by x squared minus x plus 1, which is the same thing as x minus 1 times x minus 1. So as we divide this, x squared will go into x to the fourth, x squared times. So I will multiply each term here. So x squared times x squared is x to the fourth. X squared times minus 2x will be minus 2x to the third power. X squared times plus 1 will just be x squared. So now I'll subtract negative 6x cubed minus 2x cubed. I'm subtracting a negative, so this will be minus 4x cubed. 22x squared minus an x squared will be 21x squared minus 30. So I will, so we have minus 4x cubed divided by x squared will be minus 4x. So minus 4x times the x squared will be minus 4x cubed. Minus 4x times minus 2x will be plus 8x squared. And then minus 4 times the 1, minus 4 times 1, we'll have minus 4x. So minus 4x cubed minus minus 4x cubed, those are the same, so those will cancel out. 21x squared minus 8x squared is 13x squared. Minus 30x minus a negative 4x, so those will be minus 26x after we cancel out the negative signs, plus 13. and this will be 13 times. If I divide 13x squared by x squared, I'll get 13. So after I multiply 13 times x squared, 13 times negative 2x, 13 times 1, and it divides into it evenly. So our check was good. So I have run out of a little bit of space here. So what are the factors of our function? So our factors of f, we know that x minus 1 is a factor, but it's a factor twice. And we know that x squared minus 4x plus 13 is also a factor. So ultimately, when we want to solve our function, we have these factors. So each one of the factors will set equal to 0. So if x minus 1 is equal to 0, we know that our roots, we know that 1 is going to be a root, but it's going to be a root twice, for the first factor and for the second factor. And then this last factor, we'll just have to use the quadratic formula. So if I have x will be equal to negative b plus or minus the square root of b squared. So negative 4 squared is 16 minus 4 times a times c all over 2 times a. So this will be 8 plus or minus 16 minus 4 times 32. 4 times 32 is 52, and 16 minus 52. I'll just have to do this to the side. So this will be 36, and the square root of negative 36 is 6 times I. Apologize, I've run out of space here. So x is either going to be 4 plus or minus 3i. This is just using the quadratic formula. Nothing tricky is going on here. So the roots are 1, 1, 4 plus 3i, and 4 minus 3i. Again, what we did is we found the factors of f, and we set each one equal to 0. If the first factor is equal to 0, x is 1. If the second factor is equal to 0, x is 1. It's a repeated root. If the third factor is equal to 0, this is where we get our imaginary roots. So when we come up to our picture, 1 is a root, and it's a root twice. So it has even multiplicity, so it turns around. The imaginary roots, the complex roots, aren't in this picture, because this picture only has real numbers in it. It doesn't have complex numbers in it, so we can't see the complex roots. Complex roots won't be on a graph of a function. So that's all well and good. And there's only a couple of things left in this section that I want to go through. One is the fundamental theorem of algebra, and this is going to seem a little silly based on something that we saw before. We said that a polynomial of degree n always has n roots. Well, it turns out that this is actually, this right here, the fundamental theorem of algebra, is the reason behind the previous one. So we're going a little bit backwards. A polynomial will always have at least one root. We already know that it has n roots, but this is a simpler theorem. So we know that it has at least one root. And from before, we know that if we can find one root, we can find a factor of the polynomial. And if we can factor the polynomial, we can split it apart. So if we can split our polynomial apart into one factor and then a second factor, this second factor is also a polynomial. So here's the consequence. If I take a polynomial and I factor out one factor, I look at g next, and I can factor something out of g. Once I factor something out of that, I will just continue going, looking at whatever's left over each time until I'm left with nothing anymore. So what we have is the linear factorization theorem, and this is a very powerful result, and I'll go through an example of how we might use this. But essentially it says any polynomial you ever give me, I can always factor into things that look like x minus a number. That number, those numbers are going to be the roots of f, so we can just read them off. And in fact, these could be imaginary numbers, they could be real numbers, they could be integers, rational numbers, they could be anything, but we can always do this. So let me go through an example of how we might use this. So we're going to reverse engineer a polynomial. We want it to be a third degree polynomial, and the roots are going to be -3 and I, so we know that it has at least these two roots, and we want it to satisfy f of 1 is equal to 8. Okay, so first and foremost, we know that our polynomial f is going to be a third degree polynomial, so it should have 3 roots. Well, from our theorem here, if we have 3 roots, we're going to be x minus something times x minus something times x minus something. If there's 3 roots, I know that there's going to be 3 factors. X minus the first root, x minus the second root, and x minus the third root. So far, so good. All I haven't used anything more than the fact that this is a third degree polynomial. If it's a third degree polynomial, I know that it will have 3 roots, so it has these 3 factors. Okay, so second, what are the roots? Well, we're told that one root is -3, and one root is I, but I need 3 of them. 1, 2, 3. The other really, really important thing is that complex roots always come in pairs. So this root right here, if I just do some scratch work off to the side, I can write it as 0 plus I. It's just a fancy way of writing I. If this is a root, the complex conjugate of the root, which would be 0 minus I, is also a root. Complex roots always come in pairs. One where I'm adding the imaginary part and one where I'm subtracting the imaginary part. So if I is a root, then so is -I. There's my 3 roots. I can write down my formula. F of x is going to be equal to x minus a -3, x minus I, and x minus a -I. Let's simplify this. It's going to be x minus a -3 is x plus 3, x minus I, and x minus a -I, well, that's just going to be x plus I. And then finally, we know that if I plug 1 into the function, I get 8. Great. So let's plug a 1 into my function. I'll get an times 1 plus 3 times 1 minus I times 1 plus I. Okay, so let's simplify this. This is an. This is 4. 1 minus I times 1 plus I is going to be 1 squared minus I squared. It's going to be an times 4. If I simplify this quickly, this is going to be 2. It's going to be 8 times an. But I know that f of 1 is going to be 8. So an has to be 1. And there you have it. My function is going to be this. with a n